All right, making a solution. So what is a solution? Basically something inside of a liquid. Typically it's a chemical that you're dissolving inside of water. That's the most common solvent, which is the chemical you're dissolving in. And the chemical you're trying to dissolve is the solute. So for example, if you're making salt water, salt is the solute, and then water is the solvent. That's a typical routine for these. So let's go a little bit more detail for these and see what we're looking at. All right, so what exactly is a solution? Combination of two chemicals that form a homogeneous mixture. So what does that mean? When you look at it with your eyes, it looks like it's just one thing. You can't tell the different parts in there. You can know that there's salt and water in the salt water, but you can't see it with your eyes. So it's a term that we've covered before. Just means it looks like one thing. Even though you know it's made of multiple things, you can't tell with your eyes. Can involve any state of matter. So basically you could have it in gases, you could have a solid in a liquid, you could have two liquids. There's a lot of variety in this. The most common one we're going to be dealing with is the one involving a salt and liquid, by the way. All right, so here's some examples of different types of solutions. So you can see air is one of them, which is the solute is oxygen, solvent is nitrogen. What that indicates is that the majority of air is made of nitrogen. If you didn't know, nitrogen makes about 80% of the air. Oxygen is around 20%. So obviously the majority of air is actually nitrogen, not the oxygen we need for survival, which is interesting. So you have soda water, carbon dioxide in the water, and you keep on looking at different varieties. Basically the key feature here is you have a chemical with some sort of solvent, which for most of these you can see it's water. Now there are some examples of ones that aren't, like down here. You have alcohol, silver, cotton. These are the ones that are basically alloys. Has different solids, but the most common one you can see by and large is typically water for the ones involving solid and liquid. All right, submicroscopic view of the solution. So you look at the picture and you can see that there's a lot more purple than there is red. Red is your solute, purple is your solvent. So you can usually tell the solute versus the solvent based on how much you have. The one you have more of is typically considered your solvent. The one you have less of is your solute. You can have more than one solute, by the way. So here's different examples of solutions. Coffee, which is, coffee itself. You can see there's a little cream in this one. Sugar, those all make solutes. So now you have a solution in there. Wine, different chemicals in there. Air, different chemicals. These are all examples of things that have different components. That's multiple components. That's what makes it a mixture. Chemicals with similar properties, like IMFs, behave in what's called like dissolves like, which is a simple way of saying if they have similar IMFs, they'll dissolve each other. What does that mean in English? If something has hydrogen bonding, for example, it will dissolve really well in something that also has H bonding. So what's an example of this? Let's do methanol, type of alcohol. That's CH3OH. You have to draw the Lewis structure. You can see there's an OH. So H is attached to O here. That makes hydrogen bonding plausible. It also has LDF, also has dipole-dipole. That's the whole gambit. But when you're trying to compare or determine if something will dissolve in something else, you try to focus on the strongest force. H bonds are strong, so I'm going to focus on it. Yes, it has dipole-dipole. Yes, it has LDF, but that's not the strongest. So I'm going to not focus on that. Unless you're trying to dissolve this inside of H2O, which is water, which has all three as well, right? It has H bonding, because if you draw the Lewis structure, you're looking like this. There's your bent structure. You have H bonding, you have you have a dipole-dipole, and you have LDF. So once again, I'm going to focus on the strongest one, which is H bond. This has H bond, this has H bond. They'll dissolve each other really, really well. They could also dissolve each other really, really well because they both have dipole-dipole. What if you have dipole-dipole, let's say you have this, and you're trying to dissolve it in something like C6H6. So without having to draw a Lewis structure, hopefully you all understand there's only C and H here. So that means you just have LDF. It's nonpolar. Remember, if C and H are the only elements involved, the molecule is going to be nonpolar. So this one, it's nonpolar, so you just have LDF present. So let's say you're trying to dissolve the alcohol in this. It won't dissolve. Why? Strongest force here is H bond. Strongest force in here is LDF. Yes, this has LDF, but remember, you have to focus on the strongest force to determine if it'll dissolve. Not going to dissolve. Now, if you had this had dipole-dipole and the other thing had dipole-dipole, yes, theoretically it can dissolve. But by and large, dipole-dipole and H bonding cannot dissolve in something that just has LDF. This is why oil and water don't mix. Oil is LDF only, in case you didn't know, and something like water, which has H bonding, dipole-dipole, that can't dissolve. That's why they don't mix together, because of different IMFs. So that's how you determine if two things can mix. That's how you determine if a solution is possible. You look at the IMFs, and if they're similar, yes, they'll dissolve. If they're not, they won't. All right, so here's an example of this. You have water here in the top portion. And down here, you have this nonpolar substance, right? This is LDF. This is H bond. It's called DD, dipole-dipole. All right, so you're trying to mix these solutes. This solute is an ionic compound. Ionic compounds dissolve in polar substances. It creates what's called an ion-dipole interaction. These are ions, because this will break apart into Ni2+. If you uncrisscross it, NO3-. These are ions. Ions will mix with water, which is polar, and create what's called an ion-dipole interaction. Very, very strong interaction. It's the strongest IMF possible out of all of them. It's stronger than H bonding, surprisingly enough. This is why if you have salt water, you need to boil all the water off before you see the salt again, because of this interaction. It's so strong that it doesn't break. The ions are surrounded by water and they stick to them like glue. Anyway, so if you have the nickel 2 nitrate and you're trying to put it in here, you could see it sticks to the water layer. Why? Ion-dipole interaction forms. So you're dropping this nickel nitrate, typically a solid, into this. It's going to happen right away. It's going to stick to water. It'll dissolve first, right? But then it'll stick to it. And it's a green color for the chemical. That's why this is green. You look at the other substance. We have iodine, nonpolar, right? Because you have basically a LDF only. It's bonded to itself. So that means it's going to be just LDF, nonpolar. It doesn't want to go to the water. Why? Because nonpolar and polar don't mix. So what it does instead, it goes all the way down to the nonpolar end. And that's why you see this purple color, because the iodine wants to hang out with something else that is also nonpolar and has LDF only. So this substance, remember, has LDF. LDF, like dissolves like. For this one, ion dipole, that's why it sticks together. So that's the difference between what will mix together and what won't. So this is made from ionic compounds and water. So they form ion dipole, which is mentioned. So in case you want to see this visually, this would happen. So here's the ion. This ion you can see right here is being surrounded by the water. So what happens is the water surrounds it. And hopefully you could see this is the O end, right? That's the O end of oxygen. So that's your basically your negative dipole end. The hydrogen would be your positive dipole. Remember that funny looking D symbol? These look like H. My goodness, these are ugly. Pretend these are the positive dipole ends, right? Because H is less electronegative than O. So O is the more negative end. It's got a negative dipole. So negatives surround the positive ion. Just the same way, H, which is your positive dipole end, attracts the negative ion. So they surround them and then they pull them apart. And then once they're completely pulled apart from each other, then the other H2Os come around and basically stick together. So this is an ion dipole interaction. Very, very strong interaction. You can see here what's going on. So this is just two ions instead of a crystal. Watch what happens. They'll pull them apart. And that's how you have dissolving occur. So this goes back to solubility rules now. So what if you had something like copper sulfide, right? Which we know S is -2. That's, remember, -2, -3 usually are insoluble. Water will try to surround these. They like each other more than like the water, so nothing would happen. So the solid will just stick to the bottom of whatever you're trying to dissolve it in. Whereas sodium chloride readily breaks apart. All right, solutions made of nonpolar chemicals. They mix because they both have LDF. That's the key feature. We saw that with the two chemicals earlier. Solution made of polar molecule in water. Methanol, which is a dipole interaction. In case you don't know what methanol is, CH3OH. The one we saw earlier. And hydrogen bonding is able to dissolve in water, which has DD and H bonds. So you could focus on the dipole-dipole. That's fine. What you can do is dipole-dipole and LDF. You could focus on H bonding as well. Either one's valid. Typically, you look at the strongest, and that's your focal point. But as you notice, Most things of hydrogen bonding are also dipole-dipole. So it's a secondary force and it's still strong enough to allow them to mix together. You just can't do it if one of them has dipole-dipole and the other one has LDF. That's a big no-no. So here's the methanol and how it's mixing. You can see the methanol basically sticks together and the water attaches to it through the H bond. That's how the interaction is. Fairly strong H bond. Not strong as ion dipole, but still not bad. All right, so for those that are curious about oil and water, why don't they mix? So you can see it surrounding it like it usually does. It has the negative and positives. The problem is oil doesn't have anything for it to attract to, right? There's no positive or negatives on this. So it's not so much that the oil repels the water. It's just the water rather hang out with itself. It's like you and your friends hanging out and someone that's brand new trying to hang out with you guys that you don't want to hang out with. It's not like you're trying to repel them and push them out. You just don't talk to them. You talk to each other. You go back together and hang out. That's what happens. So, oil is just unfortunate because no one's interested in chit-chatting with it. And that's what happens with most polar and non-polar substances is this kind of dynamic. They just don't mix. All right, which of the following solids will dissolve in water? Sodium sulfate. Hopefully you understand it's an ionic compound. We have a metal in the beginning. So it's going to dissociate to Na plus and SO4 2 minus. There's two NAs, one SO4, but don't worry about the quantities. That's not going to be important right now. So long story short, it's going to be an ion dipole interaction. So yes, it will dissolve. So why? Because of the ion dipole. So this is yes. This will dissolve because it will form ion dipole with the water. Gasoline, nonpolar. Well, that's LDF, right? Because it's nonpolar. Can it mix in something that's polar? Of course not. Not going to happen. So it's a no-no. Iodine. Nonpolar would mix with water, same thing as this, right? Iodine would have LDF. It does not mix with something polar. Nothing happens. HCl, this is not an ionic compound. This is what we call a molecular compound. But HCl is a very strong acid. And most compounds that begin with H, except H2O, a lot of them break apart in water. We'll talk about that much later. So for now, just accept that this particular substance will indeed dissolve in water. And it's going to form not an ion dipole, but a dipole-dipole interaction. All right, components of solutions. Solutions have two components, which are dissolving. Salt is the solute. How do you know it's a solute? Whatever you have less of is your solute, always. Sometimes they'll give it to you in terms of mass. That's how you have this many grams of salt, this many grams of water. Other times, you're just going to have to assume if water is involved, it is the solvent, because that typically is what exactly happens. So solute, which is less of, whatever you have less of is your solute. Whatever you have more of is your solvent. Those are your two components, and that's always the case. Can you have more than one solute? Of course. You can have 2, 3, 4, 5. Can you have more than one solvent? No. One solvent at a time, but the number of solutes can be different, so be aware of that. All right, so solutes characteristics. First, they mix evenly throughout the solution. So you could see initially they just hang out down here, but if you give it enough time where you start mixing it, it'll eventually evenly distribute itself. And that's what it'll look like. So this is what it is at the beginning, just sticking at the bottom. They'll start mixing slowly because the water molecules will start interacting with it. And then eventually you get to the point that they're all mixed together and you have even distribution. You can separate by evaporation. For those wondering why, H2O is your main solvent. How do you get rid of H2O? Evaporate or boil it, right? So once all the water is gone, then you'll be left with this solid chemical again, just hanging out by itself. And you get the original solid back, by the way. Because you're breaking down dipoles, by the way. In this case, it's an ionic compound, so you're going to break the ion dipole interactions and then get the solid back. You can't see them, but they can give color. Now, are all solutions colored? Of course not. But some of them are, and that's a good tip-off that there's a solution in front of you that's colored. All right, dissolving process. Dissolving occurs when solid contacts a solvent interact with each other. Increasing contact speeds of dissolving. So how do you increase contact? Mix it. Crush it. When you crush something, what you're really doing, you're exposing more of it to the water. Because if you think of a big chunk of solid, like the outside edges are always going to be exposed, right? But the inside is going to be blocked until the outside goes away. So if you break it apart into a bunch of little pieces, now you have all this exposure to water. So this can be a lot faster to dissolve because more of it. That's the long and short of how you could make mixing occur faster. There is a limit to how much solid can dissolve. It's called your solubility. Every chemical has a solubility. Consider this your max. You cannot dissolve more than this. So the solubility of a chemical could be that you can mix 20 grams of the chemical in 100 grams of water. Once you go over 20 grams in every 100 grams of water, what's going to happen? The solid will not dissolve. You'll see it sticking at the bottom. Good example, you made iced tea, you put way too much sugar, you're looking, you're mixing, nothing happens. Why? You've reached the solubility point of the iced tea. So whenever you see solid visually, you went past the solubility. Good way to impress your dates, next time you make some iced tea in front of them, or some maybe lemonade iced tea combo. Notice that the solid doesn't dissolve and say, hey, look, I reached my maximum solubility. I know. It's a great way to start a conversation or go a different direction with it. All right, so solubility. Maximum amount of solute that can dissolve in a specific amount of solvent, which can be expressed as this. So it's typically represented in grams of solid per 100 grams of water. That's the way it's represented. So this could be 20, this could be 5, this could be 60. Every chemical is different in terms of how much of it can dissolve in water. The only way to increase solubility, and this is very important, that's why it's in red, is increasing temperature. So the secret to making good iced tea or iced tea lemonade combinations is to heat up your tea and add the sugar at that point. Why? Because more sugar can dissolve in the tea at higher temperatures. Once it cools, that sugar is still in it. As a result, you get a much sweeter tea. You combine that with some lemonade, you get a perfect Arnold Palmer. Life is great. If you try to do it afterwards, not the same impact because the solubility is going to be a lot lower, so your tea won't be as sweet, and then the combination of those two doesn't taste as good. That's the really secret to finding good Arnold Palmers, is to look for a place that makes your tea hot and then adds the sugar to it right away at the higher temperature so you get a higher solubility. Because ultimately, you want sweet and sour mix. That's the whole point of ordering an Arnold Palmer. All right, so anyways, here's some examples of different solubilities. You could see from the graph and the way you read it, this is grams per 100 grams. So this is telling you that 240 grams of this will dissolve in every 100 grams of water. That's a very large number. This is at 100 degrees Celsius, which we know is the boiling point of water. But if you try to dissolve that potassium nitrate at 10 degrees Celsius, look how much you get, only 20. This is why you do sugar in hot water. Look at the big difference in the amount of solid that can dissolve based on temperature. That's what this graph is showing you, is that as you increase the temperature, except for some weird ones like down here, lithium sulfate, which is confused, goes the other way, most chemicals, as you increase temperature, you're able to dissolve more solid inside of the liquid. That's important. So the highest solubility here at 100 is this. But what if we're looking at 60? What has the highest solubility? Well, we circle this. We see what the red chemical is. And we have sodium, looks like acetate. So different chemicals are going to be high soluble at different temperatures, usually. So be aware of that. And that's how you read the graph, by the way. So if I ask you for what has the high solubility at 50, for example, you'd be like, oh, that's easy. It's the blue one. The blue one is sodium nitrate. But it varies based on temperature. All right, saturated solutions. This is you got sugar in the bottom of your cup because you added too much scenario. Anytime you see solid and it's not dissolving, no matter what you do, you went overboard. So you've reached saturation. You went beyond saturations. Actually, determining the exact saturation point is difficult because the only way to visually see it is when you're past it, right? The only way you know you've reached saturation because you went over. You see solid, it doesn't dissolve. So you can tell when you're super saturated, which is what this is. Saturation itself will be some time before this. So the exact way or time to determine is going to be difficult. You would have to have some data to tell you what the maximum saturation point is. But super saturation you can tell all the time because you went overboard. So once again, going back to your tea example with your date, your super saturated solution. See, now you're using more advanced vocabulary. Very impressive. All right, at 40 degrees Celsius, the solubility of KBr is 80 grams per 100 grams. Identify the following solutions either saturated or unsaturated. Well, if 80 per 100 is the max, right? Anything over this is going to be super. So that'll be oversaturated, really. Or you could call it saturated because there's only two options here. Anything below this would be considered unsaturated. So 60 grams per 100 grams, that's below this. So this is going to be considered unsaturated, right? 200 per 200. So you're looking at this and saying, wait a second, it's supposed to be per 100. Do the math. 200 grams KBr divided by 200 grams H2O. You get 1 gram per, because you're just going to do 200 divided by 200, right? So you end up getting 1 over 1 gram per 1 gram of H2O. You could also switch this into the same value as this by dividing both by 2. That's probably an easier way of doing it, because you want to compare it over 100 grams all the time, because that's what your data point is. This is H2O. This is going to be KBr. All right, so you can see this is beyond this, right? This is basically 100%. You're supposed to do 80% more or less if you look at the number crunching. So this would be considered saturated. Technically super saturated, but you could do saturated. It's just your answer. All right, 25 per 50. So what I'm going to do is scale this to 100 grams like I did here. So how did I get to 100 grams? I multiplied this by 2. So I'm going to multiply this by 2 as well. That's 50 grams KBr. This is 50 per 100, less than 80 per 100. So this is going to be unsaturated. All right, Henry's Law. If you ever wondered how do you get more gas in the liquid for all you soda drinkers, you already know the answer. Stick it in the fridge. Why is sticking in the fridge such a good idea? It turns out at lower temperatures, you're able to get more gas in the liquid. This is why a majority of fishing occurs in colder climates, because colder climates have more nutrients in the water, more gas and other chemicals, which in turn, more oxygen specifically. And as you have more oxygen, you have more nutrients, which means that you're going to attract more fish and they can survive longer there and more of them. So that's why you have fishing in colder climates, because there's more nutrients in the water, because there's more oxygen in the water. And this is all because of Henry's Law. So more gas dissolves at higher pressures. That's the other way of doing it, by the way. Increase the pressure. So if you increase the pressure, you're able to get more gas in the liquid, and that dissolves. And temperature can also, lowering the temperature can also create more gas. So the two ways to get more gas is going to be high pressure and low temperature. For your soda can, it's already pressurized, right? Because what they do after they make it, they put some CO2 in it to pressurize the can. That's why if you shake it or something, it fizzes and it blows up on you. Sometimes even when you don't shake it, it does it on you. But there's gas regardless there on top of the liquid. And that's to make sure you get as much gas in the soda as possible. If you want to get more gas to go in the liquid after that, you stick your can in the fridge, cools it down. All the gas is hanging out up here on top, goes into liquid. So now you have a much more gaseous soda drink. All right, that's solutions for you.